Hello students, today we will discuss about the mechanical behavior of material, in particular the elastic behavior. So when we talk about the mechanical behavior, as per the definition, it is the response of a materials under external loading condition. So first the load, second materials, and third is the response. Materials you have already studied. It could be metals, alloys, then it could be ceramics, all engineering material which we have already studied. Second, response. If I give you an example, let us suppose you are having a coin of 1 rupees and you are having a glass slide. If this both material undergo a compressive load, what will happen? This metallic coin will be drawn into some kind of thin sheet, whereas this ceramic will be fractured. So under the same compressive loading condition, both material has shown different behavior. That's what we are calling it, a response of a material. Third is the loading. Load could be of different types. It could be tensile, it could be compressive, it could be shear, torsion, or bending. So there are different kind of loading condition. To understand the mechanical behavior of material, let's first talk about the tensile behavior. To understand the tensile behavior, which will give you many of the property of that material, let's see here. Now the third thing is the deformation. Deformation, there are different kind of deformation are possible. We classify this deformation into two types. One is recoverable and second is non-recoverable deformation. Recoverable deformation means like a elastic band. If you stretched it and you remove the load, it will come back to its original position. No deformation is permanent. Whereas non-recoverable deformation is basically a permanent deformation. Here, in this further recoverable deformation, on the basis of time scale, we can further classify it time dependent and time independent deformation. The time independent recoverable deformation is called as elastic. The time dependent recoverable deformation is called as anelastic. So elastic deformation, I already given you example of the band. Now if we talk about the elastic behavior, for example, if you are sitting on a couch, the moment you will wake up, there will be some kind of impression on that couch. But after some time, you will see that that couch is recovered to its original shape. So that recovery happened in due course of time. We are calling it as an elastic deformation. Now non-recoverable deformation. If you increase the load beyond a certain limit, materials become plastic and it will not be able to recover. So that kind of deformation we call it as a plastic deformation, and time dependent plastic deformation is a one of the three. So these four deformation, elastic, anelastic, plastic and three, we will study in coming lectures. There is another kind of deformation which is called as viscoelastic deformation. This is a time dependent recoverable and non-recoverable deformation. Both occurs together. This kind of deformation we call it viscoelastic deformation. Now to understand the deformation, let's consider the typical engineering stress strain curve of a metallic material. If you have a ceramic material, then it will be like this. Here is again a strain, here is a stress like this, and here is a fracture. This is a metallic. This material is some kind of metal. So here initially, as you apply the load or stress, it elongates up to a certain range. This we call it as a elastic limit. Means the stress is proportional to the strain. You already have studied this previously. The stress is proportional to strain, and this is multiplied by modulus. We call it modulus. So up to here, you apply load, material will deform. The moment you will release load, it will come back to its original position. So this we call it as a elastic deformation. Complete recovery is there. If you increase the load beyond a certain limit, the material transforms from elastic to plastic. So this curve is basically, one is the linear one and second is the non-linear one. So this non-linear, we are calling it as a plastic deformation, and this linear portion we are calling it as a elastic deformation. So we will first study this linear portion, that is a elastic deformation. Now, what actually happened in the metals when you apply a load up to elastic limit? Let us suppose this is your two atoms closer like this. If you apply a tensile load, the bond will stretch. If you apply a compressive load, bond will compress. Then the net force here will be the force of repulsion. Here net force will be the force of attraction. We will discuss it later. So in the elastic deformation, what is happening at atomic level? It's simply a bond stretching. And this strains in the elastic material is of the order of 0.001 to 0.005. That much is the elastic strains. Now, to understand this stretching of bond, let's consider an atomic model. This curve is showing this is the force into displacement curve, and this is the potential energy and the displacement curve of two atoms, which I told you before, right? Now this is the equilibrium position where force of attraction is equal to force of repulsion. If you apply a tensile load, the bond length will increase. If you compress it, the bond length will decrease. So at this equilibrium position that we call it as a bond length is where the potential energy is minimum. So in this curve, if I plot a straight line at this point, if I plot line, or you can say tangent at this point O, it will touch up to a certain length. This is the compression, this is the tensile state. So this is basically are considered to be as elastic strains within the material. So typical potential energy equation for this kind of bond is W equal to minus A by R to the power n plus B by R to the power n. This one attractive energy term, and this one is the repulsive energy term, which is due to the mutual repulsion of atoms at very close distance of approach. And this force is equal to negative of derivative of this potential energy, where at R equal to R naught. R naught is the bond length. So F applied will be equal to minus F, that is dW by dr. So if you see here, Y modulus will be negative of dy by dr. If you see here, what does that mean? If you see this region, in the compressive state, this is the force which we applied. In the stretching state, this is the force we have applied. So if you see, the net change in force is dF, and this is the R in compression state, and this is R in stretching state. This is the change in bond length basically, and this is dF by dr. So this is equivalent to Y. This is equivalent to this is equivalent to y. So you can say y is proportional to df by dr, which we are writing it here, and this is, you can say, d2w by d2r. So here if you see this Young's modulus, what is Young's modulus? Y equal to stress over strain. What is strain? This force per unit area is strain, and stress, force per unit area is stress, and this is the strain, that is the change in the bond length. So this bond length, change in bond length and the change in force can be represented by, from this curve, can be seen at this curve. We call it, the ratio of this, we call it Young's modulus. So basically, as a summary, we can say the modulus depends upon the bond strength of the material. So higher is the bond strength, higher will be the modulus, lower will be the bond strength, lower will be the modulus. Now, to consider understanding this bond strength and modulus, I have shown a elastic portion of three different material. This is material 1, this is material 2, this is material 3. So if you see which modulus is high, of course the modulus of y1 is greater than modulus of y2, and the minimum is 3, because you are taking slope here. Slope of this is higher and modulus is higher. So you can say the bond strength of material 1 is very high compared to 2 and 3. This modulus is a parameter. To understand the property which modulus represent is called as stiffness. What is stiffness? Stiffness is nothing but resistance to elastic deformation. So in these three materials, the resistance, which is maximum resistance, is provided by material 1. So you can say it is providing more resistance to bond stretching or more resistance to elastic deformation. So the bond will be having, the strong bond will have a higher stiffness. Here one line is written: for identical shape, stiffness is proportional to modulus. This I already told you, this modulus represents stiffness. What does it mean by identical shape? Let us suppose you are having a one copper wire, and this is the copper rod. This copper wire, these are the same length. Length of these two is same. If you bend it, it will bend. If you remove it, it will again become straight. But if you bend this rod by this much angle, it will not come back to its original position. So whenever you want to compare the stiffness, shape of the material should be identical. So as I told you, as we discussed, modulus depends upon the bond strength, and so you can say, and bond strength depends upon the kind of electronic structure that atom is having. So you can say the modulus is structure insensitive property. By changing grain size, by changing dislocation density, you cannot change the modulus. Modulus is inherent property of the material, but as a material scientist, you want to tailor the property of material. So here we can design the modulus by two methods. One, you allow two different kind of material. Say one is having a high modulus material, second is having a low modulus material. So the modulus will increase proportionally. As you are increasing the composition of high modulus matter, the modulus will increase. But in this case, you cannot get the modulus of your choice. We have some limitations. We have some limitation of solid solubility. We have some limitations of secondary phase formations. Another way of designing the modulus is making these composites. So if you are having two materials, one is having a low modulus, one is having a high modulus, you mix them and you can design the modulus. I'll explain later. First, I will explain you what are the composites. Composites, these are not a solid solution. It's not an alloy. There is different kind of composites. Just to give you an example, around you, in building, probably you may be sitting in some building where there will be a beam. That beam is made up of concrete and the reinforcement is done by a steel rod. Concrete is brittle in nature as well as high modulus, but at the same time you are reinforcing it with steel because steel is having the ductility. So these are the different kind of composite material. One is, we call it matrix. Another is the reinforcement. This composite has already been explained to you in the initial classes. So we can have a different kind of composite depending upon what kind of reinforcement you are doing. Here, let us suppose this is aluminum and you have embedded particles of any ceramic material. So you can design the modulus. So if you see here, so as a summary, if you want to design lightweight but strong material, what are your choices? Of course, aluminum is the one of the lightest metal in the periodic table, but it is very, very ductile. Another way, boron, which is very, very strong, but it cannot withstand extend loading because it is brittle, so its modulus is high. So by this rule of mixture, you can design the modulus. This VF is the volume fraction of fiber or reinforcement. This is volume fraction of matrix. This is modulus of fibers. This is modulus of matrix. In this case, if let us suppose you want to make a composite 70% of aluminum and 30% of boron in the particulate form, then the Y will be of composite will be 0.70 multiplied by 71 plus 0.30 multiplied by 440. This will be your final modulus of the composite.